Annulenes are cyclic molecules with alternating single and double bonds. The number of carbon atoms in the ring is placed in brackets before the word annulene when naming these structures. So here we have three examples of annulenes. The first molecule, which we've seen previously, is known as Cyclo Butadiene, but it could also be called 4-annulene. Benzene could also be called 6-annulene, and cyclooctatetraene could also be called 8-annulene. The next annulene in the series is 10-annulene, an isomer of which is shown below. At first glance, this may appear to be an aromatic molecule because it has 10 pi electrons, which is a 4n plus 2 value when n is equal to 2. But remember that before considering the number of pi electrons in the system, we must first ask whether the molecule has a continuous cyclic array of parallel p orbitals. Well, this compound is certainly cyclic, and there is a p orbital on each and every ring atom. However, it turns out that the ring is not planar. The reason is the repulsion of the hydrogen atoms in the center of the molecule. The central cavity is not large enough to accommodate them, so the ring must bend out of planarity. Since the ring is not planar, this 10-annulene is non-aromatic. The diagram on this slide highlights the central hydrogens, which are problematic. They're the ones that cause the ring to bend out of planarity. They are not drawn with the desired 120-degree bond angles because they would literally overlap with one another, highlighting the problem. They've been skewed to the sides simply so that you can clearly see each of them. A similar problem arises with 14-annulene, which is the next annulene with a 4n plus 2 number of pi electrons. This molecule can achieve planarity, but the repulsion of the hydrogen atoms directed into a relatively small central cavity diminishes the aromatic stabilization. The next annulene with a 4n plus 2 number of pi electrons is 18-annulene. It has 18 pi electrons. This molecule's central cavity is large enough to accommodate all the hydrogens that reside inside it, so it can achieve a nearly planar conformation, which it allows it to enjoy aromaticity. The next video in this series will continue our discussion of aromaticity with polyaromatic hydrocarbons.